I'll apologize to Noah for not having any equations in my talk. But yes, this work has been done by me, myself, mainly our PhD student, Ji Lang, and Luke as well. Okay, so let's start with what ice shelves are. Had a nice little introduction before, but we'll just revise some of that. So this is a picture of an ice shelf. We have our open ocean to the left, and we have this ice shelf to the right, this consolidated mass of ice, which with this nice helicopter for scale, we can see it sits quite high above the ocean. Although for those familiar with ice and water, this is just the tip of the iceberg, as it were. And when we look at a cross section into the ice shelf, we get something like this. So we have depth being our vertical scale and our distance into the shelf being our horizontal scale. So this is ice shelf data that we have. And as I said, we can see most of that is below the waterline. And indeed, the ocean continues under the ice shelf, and the ice shelf actually floats on top of that ocean. So ice shelves tend to be hundreds of meters thick and can be up to hundreds of kilometers long, as in this example, although they can also be shorter as well. So this is a large mass of ice. Where does it come from? Well, it's essentially fed by the Antarctic Ice Sheet. The other plot about buttressing was very good for demonstrating this, and will be fed into this. But this is the Antarctic Ice Sheet, and we can see the ice shelves, which are colored blue when they're very thin, closer to the ocean, and thicker reds closer to the land. And indeed, the ice sheets flow out onto the ocean and become ice shelves. And we're interested in the ice shelves due to this buttressing effect they have on the ice sheets that feed them. And when ice shelves disappear, we find that the ice sheets that feed them flow much faster. And this, of course, has implications for sea level rise under climate change. Another reason that ice shelves are very interesting is because the ice sheet here is exposed directly to ocean dynamics. And so we'll get the transport of heat and salinity around the ice shelves, around the ice sheet at the ice shelf area. And importantly today, of course, is going to be ocean waves. So this is a very simplified picture of a wave. We have an amplitude or a height, which is twice the amplitude, and a wavelength being a distance over which our wave repeats, and a period being the duration over which the wave repeats. And we're going to talk about two types of waves today. Wind waves, which will be the waves that you immediately pictured when I said ocean waves. Ones generated by wind blowing across the ocean. And these have periods in the order of 1 to 30 seconds, and wavelengths correspond to 1 meter to 1,500 meters. And their amplitudes tend to range from half a meter for very calm seas up to 8 meters for very rough seas like we see in the Southern Ocean. And then there's this other type of wave, infragravity waves, which are caused by the interaction of wind waves with coastlines. And they're much longer waves. So their periods are 30 to 600 seconds, and their wavelengths correspondingly in the order of kilometers up to hundreds of kilometers. So they're huge. Fortunately for us, I guess, their amplitudes are much smaller. So they have amplitudes of 1 millimeter to 20 centimeters there. So think about the two classifications really as our short waves being our wind waves today, and our long waves being our infragravity waves. Yeah?
Just a silly question. So to talk about infragravity waves or wind waves that hit the coastline. Is that right?
So there's some kind of complex interaction between the wind waves, which generate these harmonics at higher harmonics that then travel as free waves in the ocean and become unbounded. I'm not really an expert, no. Okay, so the point of the waves being is that we have an ocean and we have some waves. And as Fabian pointed out, the sea ice does act as a buffer, but over the course of the year, the ice shelf can be exposed directly to ocean waves, even though sea ice tends to attenuate them. And so here's the example I've got here of the open ocean. Our waves come in from the left, hit this ice shelf, and it's not perfectly rigid, and indeed will vibrate. And so we'll get something like this. We will get some reflection back, generates more ocean waves, not really caring about that today. And then we have our vibrations in our ice shelf, which will be our flexural waves. And I've drawn them both as waves in the shelf and waves in the water cavity to denote the fact that the ice shelf and cavity are completely coupled in the wave motion. So sometimes in the literature, these are therefore referred to as flexural gravity waves to denote flexure, ice, gravity waves, water, essentially. Now that we have our ice shelf vibrating, we can start to get mechanical deformation due to the cyclical loading of these vibrations causing stresses and strains. And this was proposed as a model for fracturing in this 1978 Nature paper, which is now a bit historic. But in that paper, they're really just vibrate the shelf and then see how much vibration you'd need and where you'd likely see fracture. But today we have some more interesting examples correlated with the exposure of real ice shelves to wave energy, I should say. So in particular, we have carving event, which is one example of fracture. There's many processes that lead to carving, but fracture is one of them. And this was the ice shelf to the north, and it was completely consolidated, and then this carving event happened, and we had the generation of these icebergs here. And in this paper, they associated that with the wave energy due to the arrival of the Japanese 2011 tsunami, which is why it's printed in 2011. And then more dramatically, we have our disintegration events. So this was the Larsen B prior, and then in a month, very quickly disintegrated and created this. So Masamo et al., this Nature paper points out that although there are many factors, one of the ones that he wanted to highlight was that this was associated with the exposure of the Larsen B to wind wave energy. So we're really interested in flexure and vibrations in ice shelves because of their implications for their integrity. But what we don't have here is a model for flexure from ocean waves. They just kind of assume that the ice shelf's vibrating. So we need to actually get a model to transfer our energy from our ocean into the ice shelf. And that's what we're going to talk about today mainly. Okay, so these are our two properties. We have our waves and we have our ice shelf. And I've drawn our ice shelf as two-dimensional because it is a two-dimensional model that I'm talking about today. Although, of course, real ocean waves, real ice shelves are three-dimensional. We have our thickness and our cavity depth, which changes over the distance into the ice shelf. And then we're going to want to send our wave in, essentially. And I already drew you a conceptual model of what it's going to look like. We get some reflection and transmission, but I've actually been overly simplistic. So the waves are supported because the medium, in a uniform medium, that's when we can talk about waves. And the medium is defined, and the medium changes every time our thickness and our cavity depth change. So really, I'd have to draw a reflection and transmission problem every time my cavity depth and my thickness are changing, which would make a horribly messy picture, which is why I didn't do it here. But that is precisely what the model does. We break our ice shelf up into uniform segments and then solve that approximate the geometry well, and then solve a reflection and transmission problem at each of these interfaces. And that allows us to get the displacement and strain at each location in the ice shelf for any incoming wave. So you give me a wave, a regular wave with an amplitude and a wavelength, and I can give you the displacement and strain at each location. You'll notice, however, that my ice shelf is really realistic, or it looks like a real ice shelf, and indeed it is, taken from real data at least. But my waves are very regular. So real ocean waves don't look like regular waves. Instead, they look something like this. So I plotted my ocean waves over distance, which is different to how most people plot them. They usually plot them over time, but I've done that just because I'm going to plot profiles, but it's the same. So anyway, the amplitude and the periods are all random. It's all stochastic in there. And indeed, we don't have a strict bound anymore on the heights of waves. Instead, what we tend to measure is the significant wave height, which is a statistical measure, but does correspond roughly to the mean of the highest 1/3 of waves. And you can kind of see how it acts as a loose bound on how high we expect waves to be in the ocean. So to actually study these ocean waves, what we're going to do is what we do with ocean waves all the time, is do a linear decomposition into its wavelengths via a harmonic analysis. So at the top, we have our long wavelength components, and I've only plotted finely many because, of course, there's lots, and you can pick some number, but you pick enough to be able to approximate your signal well. So at the top, we have our long wavelengths, and they have a short amplitude in our signal, and then my wavelength decreases as I go down the plot, and I have increasing amplitude at first, and then decreasing amplitude. So now I have my regular waves, and I have an ice shelf, so I can solve that problem. Looks something like this. I guess the thing that I did that's a bit tricky is that I did have to change the distance scale. So the wavelengths look like they've changed, but they haven't. I've just zoomed out. But anyway, so we can solve for displacement at each location for the incoming wave components. And then we can, from that, get our statistical measure of our significant height over the profile of the shelf. And that looks like this. So we can see we get more displacement at the edge because we have the free edge conditions there. And then we also have increased displacement where the ice shelf is thinner. And this makes a lot of sense because elastic bodies, when they're thinner, they flex more. Essentially, you keep that Young's modulus the same. And we also have a bit of it's pretty uniform though, and the shelf's pretty uniform in thickness, although we do see a bit of a decrease at the grounding line. And since I mentioned it, I will mention that my grounding line here doesn't actually exist in my model. I've just kind of chopped my model off early and then let it go out to infinity to avoid reflection. So just full transmission. There's a lot of debate in the community about that, so we'll just skip over that. But the important thing is I now have my model, which is full non-uniform shelf and irregular waves, which haven't been done before. So pretty happy with that. But we have a model, doesn't mean it works. So that's where we're going to next. So here's our Ross ice shelf. I'm going to validate our model by comparing it to data. And that's where it's situated in Antarctica, although it sounds like I hear a lot about the Ross ice shelf, so you all know where that is. So here's our profile that we'll be interested in today. And the reason we're interested in this particular profile is because it connected two locations where measurements were taken both in the ocean and in the ice shelf. In particular, those red dots there, which aren't very clear, although you can see one in the ocean and one on the ice shelf. And the ice shelf's huge, so although they're kilometers apart, they don't look very far apart on the whole profile. But it's good that they're close to the edge so that we can really get a sense of the vibrations there. So that's what this Chen et al. Paper did, was to plot the displacement in the shelf as divided by the displacement in the ocean. So there we fixed our location for our displacement, and assuming it's linear, which is a good assumption, a fairly good assumption, then we've also fixed our amplitude as well. So now it's just a function of frequency, this ratio. Amplitude being fixed by dividing by the displacement in the ocean. And then we have our average and our 95% confidence interval. And I guess we plotted in frequency, although I've talked about period, but that's the relationship there. Okay, so I'm going to talk about it by breaking it up into our short and our long wave regimes that I already mentioned. So wind waves are actually kind of off the plot, but we can see a little bit of it there. So the wind waves being shorter. Oh, I swear I didn't do that. It just ended. Yeah. That's fine. We got a bit of time to kill, right? Okay, yes. So our wind waves. I don't know what's happening there.
The next slide.
Okay, yeah. Oh, is that the way to go? Yeah. Okay. So, talking about this, wind waves, low periods, high frequency. They're mostly reflected. So what you see in the plot is that for displacement in the ocean, you don't get much corresponding displacement in the shelf. So the ratio is low. As our period increases and our frequency decreases and we head into the infragravity regime, we start to see more displacement in the shelf compared to how much displacement we get, corresponding displacement we get in the ocean. And it kind of plateaus out to almost 1, although it's a bit less than 1. And then, of course, we can model this profile, this transect in our ice shelf. And we've also done a bunch of others to try and account for different wave directions that are possible, since my model is two-dimensional. And also, unfortunately, the changing ice shelf locations as well, since there's a bit of a difference between when the measurements were taken and what the bed map data looks like now. But doing that, you get something like this. We get our average and we get our standard deviation. So I guess the basic thing is, firstly, it fits within the 95% confidence interval, so pretty happy about that. And then it also follows the measured average kind of well. And we're pretty happy about this as well, because it does, like our model, like we'd expect maybe, for the longer waves, we do get full transmission out to 1, which we would expect for really long waves, but hasn't been seen in the data. Okay, so that's great. Now on to like a more interesting picture. So instead of looking at just a line, or maybe an average of lines as I did before, we're going to look at a region, which actually again is going to be an average of lines. But this region is going to be plotted like this. I'm just going to rotate it. You can see that my ice edge has been maintained. I'm just rotating a bit. That's an example of what that looks like, the thickness. And then I'm going to send in waves for a variety of directions, although pretty close to perpendicular to this to a kind of approximation to the ice shelf edge. This is to account for different wave directions, but also trying to keep waves pretty perpendicular to the ice shelf edge. So that's what I'm going to do. But first, I'm going to describe the interesting features in the ice shelf to look for in the strain maps that I'm going to produce. So we have our thickness, which goes from thin ice being pinks up to thicker yellows, and then our cavity depth being low with the blue and then being higher for the greens. So the interesting features in thickness are these four. We have these kind of bottom crevasses, which run almost parallel to the ice shelf edge. We have this region of really thin ice towards the edge of the ice shelf. And then we have this region of very thin ice shelf at the edge, which then extends into the ice shelf as well a little bit. So it's really thin at the edge, but then you kind of get like a little tail to that. These features are also in the cavity depth, and we can see the cracks quite clearly, the crevices. And then this region here, very thin ice as well. And this is because the bed changes over much longer scales than these features. So the bed's essentially flat. Your ice is thinner, so you get more water underneath. The features that in the cavity depth that aren't those are these three, which correspond to a rise, like a V-shaped rise, and this region up the top here, a very low cavity depth, as well as this region here. Okay, so now we're going to do typical wind waves for the Southern Ocean and send them into our shelf at a variety of directions, average over the directions, and look at the strain. So that's what I have here. We can see the strains give us our color, and they go from 0 to 2 times 10 to the -7, which seems quite small, but when you consider that our Young's modulus is 10 to the 9, roughly, for ice, it's actually quite significant stress on the ice shelf. So we have the interesting features about this. Firstly, I mentioned how liney it is. So this has to do with the ice shelf edge, the edge of the ice shelf determining very strongly how much waves get into the ice shelf in this frequency range for waves. So once it gets into the shelf, though, it travels pretty easily. And so you get the line showing up very clearly where it met very thin ice at the edge. And so you can actually see that I've used about 5 directions to approximate this. Then the interesting features are going to be these features in the thickness. So we can see this bottom crevasse and this one quite clearly, and most particularly this region here, very thin ice. And this is because it was close to the edge. And so a lot of the waves got in due to how close it was to the edge and generated very high strains on our ice shelf, as well as this region over here as well. However, what we don't see really is the cavity depth changes in this plot. We don't see any effects from the cavity depth up here or over here or over here. This is in contrast to our longer waves, our IG waves, which look like this. Most of the waves get in, which is kind of what we saw in that Chen-et-al plot, the transfer function. And there again, we can see some cracks here. We can see that crack, and then this region of very low thin ice. And now, in addition to those very regions of very thin ice, we can also see these regions of very low cavity depth as well, which we didn't see in the wind wave spectrum. And this is kind of what you'd expect for longer ocean waves. When waves are long compared to their depths, they tend to feel depth effects very quickly, whereas when they're short, they don't really see the depth at all. It's almost infinite for them. But these are quite nice results, and it's the first time it's really ever been measured, so pretty happy about that. That's really kind of where I finish up. Thanks for listening.